memoryless. Memoryless property of exponential distribution. Now, let me tell you this. The memoryless property is going to say the probability that an event is going to occur in the future, okay, does not depend on any past information. That's what we call memory. It doesn't have memory. Exponential doesn't have memory. Okay, let me give you this example. If you take a look at this electrical material now, okay, the probability that this is going to fail in the next hour does not actually depend on how long it has been in operation. That's what I mean. Does that make sense? Okay, it doesn't depend on how long it has been in operation. And what is the mathematical implication of that? What does that mean? Do you know that that means if I have a random variable t, that happens to be a duration of time. So what I mean, the conditional probability, okay, of days given days is the same as this. Okay, let me tell you what this guy means. The conditional probability that events occur after the additional time s, after the additional time s, given that that event does not occur up to time t, given that it doesn't occur up to time t, is the same thing as the probability that event occur after that time s. How can we prove this? Okay, now I'm going to show you now. If you want to prove this, the idea of a conditional probability will actually be used. Do you remember this that we've done before, right? I'm actually going to call the whole of this A, the whole of this B, right? Okay, now I want to find the probability of A given B. Then I need to look for what it is. So I'm going to do this right now. Okay, I'm actually going to do this right now. Okay, the probability of t greater than t plus s, okay, given t greater than that, okay, now it's going to be the probability t greater than t plus x, okay, intersection t greater than that, okay, divided by the probability. Who does not understand this? I'm actually applying this conditional probability rule. Okay, now I want to award an extra credit now. Can somebody tell me for an extra credit what is common between this and this? Can somebody tell me which one is common, like intersection? Can somebody tell me? Okay, which one? Okay, let me do this. If I have this, s greater than 8 and s greater than 6. So which one is common? Which one is the point of intersection? Can somebody tell me? Is it you say greater than 8? Yeah. Okay, so which one? It's like greater than 8. This guy is common. Okay, now let's see. Greater than 8, 9, 10. Greater than 6 is also going to include 9, 10, right? This is common. This is the way I understand my maths. I need you to listen now. If I want to go by this, it may not make sense to me until I do this. Doing this, because t plus s is greater than t. Then I can just put numbers. It will be super cool pointing out that this is going to be this, right? Then divided by this right now. Okay, take a look at that. What do you see? Oh my God. If you take a look at this, the idea of a CDF can be used. If you take a look at this, greater than is going to be 1 minus. 1 minus what? Less or equal to, right? Do you see what I'm saying? Okay, law of complement, 1 minus. T less or equal to, right? What is this? That's a CDF, right? You remember CDF? That we did. So this is going to be like 1 minus f of t plus x divided by 1 minus f of t. Okay? That is what it's actually going to be. But you know what I want to leave it with? Okay? I want you to prove. I want you to use the distribution now. Okay? In terms of t, because t is a random variable here, it means f of t will be 1 over beta exponential raised to power t over beta, t greater than 0. If you want to find this guy, now please pay attention. If you want to find this guy, let me look at my time. Oh, 45. Okay. If I want to find that guy, you know what I'm going to do? I need to first get a CDF. What is a CDF? The probability of this less or equal to that, which is going to be from the lower bound to t of the distribution. Okay, maybe I can call this x now. Okay, now when you take a look at this, 1 over beta is going to come out. Then I'm going to have 0 to t, this, dx. What is going to happen? Okay, this guy is going to be divided by minus that 0 to t. Do you see that? I'm seeing something now. This guy, cancel that guy. What do I have here? Negative this from 0 to t. Okay, so if you have that, what would be the next one? If you have that now, what is going to be? Okay, this is going to be negative this, negative t minus, okay, 0, right? What is going to be? Right? What is the f of t? This is the CDF of an exponential distribution. Now, if I want to apply it here, okay, what am I going to do? 1 minus, what am I going to plug in? T plus s. Wherever I see t, I'm plugging in t plus s. Now you're going to see what I'm going to do now. So that's going to be 1 minus t plus x, right, divided by b, okay, divided by 1 minus, okay, what is the f of t? 1 minus this. Do you see that? If you try to simplify that, that's what we want to do right now. We want to simplify that guy now. Okay, we want to simplify that guy now. Okay, that's going to be 1 minus 1 plus e raised to power negative t plus x over beta divided by 1 minus 1 plus this guy, right? This cancel that cancel that, right? So right here, this can be splitted as this. Oh my God. What does that give? That gave this. And do you know what I got? You know what this guy mean? Okay, if I want to take a look at this. If f of t equal to this, and don't forget your f of t is this. Is this. If it is this, then what is the complement? What is the complement of that? The complement of that is just going to be this, right? Therefore, here, this guy is this. Is the probability of that. And that's exactly what we said we want to prove. We said we want to prove the probability of this greater than t plus s, given that this. What we just proved now is that it is this. That's what we call a memoryless property. Okay. I'll quickly go to another